Good morning, everyone. The topic for this webinar is meta-analysis, what, why, and how. Meta-analysis 101, what, why, and how, conducted by Hassam Waheed. Let me introduce Hassam first. Hassam Waheed is a PhD student, PhD candidate in Faculty of Business and Law, Taylor's University, under the supervision of AP Dr. Rotnes and Said. Yeah, I'm the co-supervisor of Hassam. Hassam's doctoral research investigates behavior interventions in the Malaysian retirement market through an experimental design. He takes a multidisciplinary approach to his research that entails the fields of social psychology and behavioral economics. Hassam holds a Master of Business Economics degree and a Bachelor of Business and Commerce degree from Monash University, Australia. He has published Scopus Index papers and he has held several external grants. Currently, he's working on several meta-analysis projects. So Hassam, hopefully, his seminar is this week, and hopefully he will be a doctor very soon. And I invited him to conduct this session because I'm very interested to know more about meta-analysis. And we have a few papers on meta-analysis. I'm not sure what software Hassam, I'm not sure even whether he wants to use any software today, but he's an expert in R, and now we know what will be the next webinar. The topic for the next webinar, it will be an introduction to R by Hassam Waheed, but by that time you should be Dr. Hassam Waheed. Okay. Thank you very much for accepting my invitation, Hassam. So yeah, the stage is yours.
Right. Thank you for the lovely introduction, Dr. Said. And thank you so much actually to the whole committee of PLM for organizing such insightful webinars. I'm actually grateful for that. So yeah, let's just dig in, I guess. So what I will do is I'll try to finish this whole presentation in about 40 minutes or so that we have roughly 20 minutes for question and answers. So with the meta-analysis, what I have found out so far is that it gets much easier as you go, as you actually practice it. And if you ask,
Hassam, can I add something? Yeah, for those who are participating, just I want to add one more thing before Hassam starts. You have a very high chance to publish meta-analysis paper compared with empirical studies. So for those who are interested to publish a paper, this can be maybe a shortcut. Actually, it's not easy to publish. I mean, in terms of the analysis, you need to be patient. The method is not that difficult, but you should be patient. But you have a very high chance to publish a meta-analysis paper. Sorry, Hassam, it seems I'm taking on behalf of you. Okay, please proceed. Thank you very much.
Thank you, sir. Feel free to come in anytime. I actually don't mind that at all. So yes, Dr. Said is absolutely right. It's a bit easier to get a meta-analysis paper published because it takes a lot of effort, and for reasons that I will explain later. So yeah, this webinar is on meta-analysis. It's supposed to be introductory in that sense for anyone who has not conducted a meta-analysis before. So the aim of this webinar is to introduce you to what a meta-analysis actually is. Why do we conduct a meta-analysis, and fundamentally how to conduct a meta-analysis. So yeah, let's just get into it. So yeah, a basic overview first. So there are two main authorities on a meta-analysis. The first is Wilson and Lipsey. Actually, if you see the top most published meta-analysis papers in the top journals, 80% of them will have cited Wilson and Lipsey. So their practical meta-analysis book is what researchers in social science actually follow. So this is a very comprehensive book that has given protocols for how do you actually do a meta-analysis. And if you don't cite their paper, especially in social sciences, and you try to publish a meta-analysis, you will be questioned on your protocols. What protocols have you followed for the meta-analysis itself? So it's important you cite them and you follow their protocol specifically. So this whole presentation is actually from their book itself. I've taken excerpts from their book because they're the experts, and it kind of makes sense also. And second is Rosenthal. He's the one who basically founded the contemporary approaches to meta-analysis. It might be worthwhile to check out Cochrane reviews as well. They're experts in systematic reviews and meta-analysis as well. They're a huge database. So this webinar will start with an introduction first, followed by a problem specification, basically your research problem, formulating a research problem. The third part is by far the most fun part, which is the statistical part of extracting effect sizes and what statistics do you basically need to conduct a meta-analysis to begin with. The fourth part is coding. When I say coding, coding basically means formulating a formal systematic technique of noting down every single step involved in the meta-analysis. This is actually very crucial to a meta-analysis, which is why it's one of the most popular techniques. And finally, there's the analysis part. So yes, this webinar itself is based on two assumptions. One, I'm assuming participants have a solid foundation in statistics. Really, there's no way around this in a meta-analysis. You do need to have a solid foundation in statistics. Secondly, you must be at least aware with the core tenets of experimental-based designs. Even if you're not, it's fine. It's okay, I'll introduce you to it. But a meta-analysis basically follows these two assumptions. You need to know these two before you carry out a meta-analysis. So yes, start with the introduction. So a meta-analysis is basically a quantitative way of aggregating past research, related research, to arrive at new conclusions. So there are a few core tenets of a meta-analysis. The first core tenet is that it is quantitative in nature. The second is that the methodology that's employed is very methodical. Everything is very systematic and everything is noted down, and it's actually included in the method section. From the introduction to the analysis part, you basically write everything in the method section of how you went about to do your meta-analysis. The third core tenet is the aggregation of past related studies. This is the fundamental nature of meta-analysis, that you aggregate and combine past studies that are conceptually similar. And fourthly, it's past research, which is combined. And finally, you reach at new conclusions that are not only included in the studies that you're aggregating, but the whole point of doing a meta-analysis is that you create new knowledge using those past studies. So an easy way to understand what a meta-analysis is that you can conceptualize it as a form of survey research in which the research reports or the studies that you're including in the meta-analysis are being surveyed rather than people itself, which also basically means that you do have a questionnaire, and that questionnaire is your coding form or the coding part. So it's very similar to survey-based research in that way. So since meta-analysis focuses on aggregation of different studies, there are two further assumptions: that all the studies that you are including have to be conceptually comparable, which basically means that the relationships that you will be examining have to be of the same constructs. This is a very fundamental assumption of a meta-analysis. And secondly, since every study reports different statistics, you will have standardized beta values, you will have unstandardized beta values, you'll have p values, you'll have f values. But how do you aggregate so many different statistics given in so many different units together? This is something that the meta-analyst does himself or herself, is basically convert all those units and statistics into one statistical common unit and then combines the studies together. So this is actually the most tiresome part of a meta-analysis. The rest is relatively straightforward. So a brief history on meta-analysis first. The first formal technique that was actually employed to combine studies was actually spurred from a typhoid vaccination study in which a researcher, basically Pearson 1904, sought to combine studies that had the intervention of typhoid vaccination. So his main purpose or primary motivation for combining these studies was that individual studies that actually did assess typhoid vaccination's efficacy were too small in terms of the sample size. So he thought that you cannot reach any definite conclusions with such small sample size. So there's a need to combine those studies so that the sample size increases itself. Though this was not a meta-analysis per se, but it was the first known formal way of combining studies statistically. The contemporary approach to meta-analysis was by Glass and Smith, Smith and Glass, 1977. They actually coined the term meta-analysis, and basically it started off with 375 psychotherapy studies that they combined to reach an outcome of whether psychotherapy is effective or not. So this is the first known meta-analysis, and they are the ones who coined the term. Contemporary approach to meta-analysis essentially follows Smith and Glass. So some key concepts of meta-analysis. So central to a meta-analysis is what's known as an effect size. An effect size is your dependent variable in meta-analysis. Without an effect size, you basically cannot do a meta-analysis. So the whole point of doing a meta-analysis is that you look at an effect size. Effect size is a simple way of quantifying differences between two groups. So let's say you have a treatment or an intervention. So control group that does not receive the treatment and the treatment group that receives the respective intervention, you compare those two groups. And the difference between those groups is basically, when you standardize those differences, it's known as an effect size. Effect size is something that tells you the magnitude and direction of relationship. So we're all familiar with p-values itself. P-values are not very central to a meta-analysis, though it is included. It has its obvious benefits. But according to the American Psychological Association, even it's mandatory in some journals, top journals, especially in psychology and social psychology, that besides p-value, you have to report confidence intervals as well as effect size. Because the problem with p-value is that if you have large enough samples in your study, you will almost always find a significant p-value. So an effect size is something that tells you the direction and the magnitude of a relationship, but a p-value does not do that. So even if your p-value is insignificant, an effect size is something of more importance when you have intervention-based studies. So yes, central to a meta-analysis is the notion of effect size. So keep that in mind as we progress. So the whole point of doing a meta-analysis is to increase the statistical power and precision to detect an effect. So meta-analysis increases the precision and power of the study because you accumulate and aggregate a host of different studies. Let's say you include minimum 2 studies, even then your sample size would still be greater than the one included study. So the greater the sample size, the more precise your estimates would be in this case, and the more power you will have to detect a specific effect. So that is one of the purpose of doing a meta-analysis. The second point of doing a meta-analysis is to identify potential sources of heterogeneity in relationships or effect sizes that you find in past related studies. So statistical heterogeneity basically means variations in effect size. So one study might report a small effect size and other studies might report moderate effect size. So this is classified as statistical heterogeneity. And to find why do different interventions have different effect in different studies, that's what a meta-analysis identifies the sources of that sort of heterogeneity in the effect of an intervention. The third point of doing a meta-analysis is to reduce subjectivity of study comparisons. Now, since a meta-analysis is very methodical in nature, since you note down every process or details of how you conduct a meta-analysis, it then becomes a yardstick for future researchers to compare their individual study against. So in that way, a meta-analysis is very useful. Fourthly, a meta-analysis identifies a gap in the knowledge base. So this is also very useful for future researchers then. And finally, actually this list is pretty long, but I'm just listing the main points that you will see in literature as well. And finally, a meta-analysis is very useful for calculating sample size for your studies or your research or potential research studies. So central to calculating sample size is power, which is 1 minus beta. Beta, in this case, is type 2 error, probability of rejecting correctly, probability of correctly rejecting a false null hypothesis. So you want to decrease this probability of falsely rejecting this hypothesis. And in social sciences, this is set at 0.80 or 80%. And p-value is set at 0.05. The only unknown variable then is the effect size itself. So once you determine the effect size from a meta-analysis, you can then potentially calculate sample sizes. As a general rule, the larger the sample, the larger the effect size, the smaller is the required sample size. So with larger effect sizes, it means that it's more pervasive within a particular population, so you can easily detect it then even with a smaller sample size. So these are the 5 main purposes of conducting or doing a meta-analysis. So putting meta-analysis in context, considering the hierarchy of scientific evidence, meta-analysis actually tops that, including systematic reviews. So the whole reason why this tops the hierarchy of scientific evidence is because you aggregate so many studies and you reach conclusions by increasing statistical power and precision. So meta-analysis is then considered a gold standard in scientific evidence in that way. So a lot of researchers first look at meta-analysis when they're doing their own research, and then they would move on to look at randomized control designs, correlational-based studies, and so forth. And another way of looking at a meta-analysis, if you compare it with traditional reviews and systematic reviews, is that a meta-analysis consists of a team. You can do it individually as well, but because there's so many steps involved, it's better to do it as a team rather than individually, compared to other reviews, traditional reviews, for example, which can be done individually. The thing with traditional reviews is that it's very subjective. A meta-analysis reduces that subjectivity because of protocols established. So if you want to get published, a traditional review is very hard for an emerging researcher because he or she is not very well known in the field. And a reviewer would basically consider someone who is an expert in the field because his or her judgment would be more accurate than someone who is an emerging researcher, coming up researcher. That's why a meta-analysis is something that can be done by a new researcher himself or herself, because you list all the protocols. So as long as you list it down and you've done it correctly, you have very good chances of getting published. So a meta-analysis follows a protocol and it's based on statistics. Moving on, so this shows, this figure 2 over here shows the meta mass production, how meta-analysis has been gaining popularity since 1986 to up until 2014. Actually, I couldn't find the data till 2019, so I listed till 2014. So there's been an exponential increase in published meta-analysis. Part of this reason why meta-analysis is being published a lot is advances in statistical softwares. It actually eases the process of conducting a meta-analysis. So moving on to the second part, problem specification. So like any research, meta-analysis also needs a research statement that needs to be carefully formulated. So I've listed down 3 examples. All these 3 examples are actually very good meta-analysis papers. I would recommend everyone to read them if you're interested. The first one, the research problem in the first study, or the research question rather, is do financial education programs improve financial behavior? The third meta-analysis research question was how effective are smoking cessation regimes? And the third one is which healthy eating interventions work the best? So what do all these 3 research questions have in common? Firstly, they identify and fill a gap in literature. I mean, every research fundamentally does that, but this is very central to a meta-analysis. It's the main reason you would conduct a meta-analysis. And this gap in literature is in the form of heterogeneous effect sizes or relationships, or conflicting evidence, as well as an unsettled state of literature. Actually, it's not that when you go out to find a research topic to assess, it's not that it's already given. It's something you have to formulate yourself. When you're very familiar with a particular topic, you go in and you formulate and extrapolate the gaps yourself. And it's something that the way you write that gap then makes it important and makes it publishable then. So the second commonality between all these three research objectives is that they examine the effect of an intervention on a conceptually similar outcome. This is actually important. So reverting back to the three research questions. So the first one, the intervention is financial education programs, and the outcome is financial behavior. In the second research question, smoking cessation is basically the intervention, and it's sort of self-explanatory over here because the word smoking cessation is there, so the outcome itself is smoking cessation. And in the third one, which healthy eating interventions work best, the intervention, as evident by itself, name itself, the healthy eating is the intervention, and works best is basically the outcome, basically which one makes someone more healthy. I suppose that's the outcome in this case. So an intervention is basically part of experimental designs to establish cause and effect. Conceptually similar outcomes, this is something which you would know more in your research area. So just to give you an example, financial behavior consists of several different subdomains, for example, savings, financial planning, borrowing, and so forth. Now, financial planning, borrowing, budgeting, these all can be conceptualized as financial behaviors. So it is essential when you conduct a meta-analysis, your outcomes be conceptually comparable. You cannot, for example, compare financial outcomes with financial behavior. It has to be one specific domain. So yes, moving to this example, what if we wanted to examine the effectiveness of financial education on financial outcomes, as I was mentioning? So this is something that you cannot do in a meta-analysis because your your outcome in this case is too broad. Your DV is too broad in this case. It has to be more specific. So in this case, you would do what's known as a systematic review. For example, there's exactly a systematic review that had this research question. So this problem is actually termed as comparing apples and oranges when your outcome is too broad. So you need to have a dependent variable that is conceptually more narrower in that respect. So the first step is when you are downloading your studies or you want to basically compare different studies, is that you need to establish a study eligibility criteria. So there are a few distinguishing features that establish an eligibility criteria for your studies. Basically, this means what studies are you going to include in your meta-analysis. First is you need to see the nature of the intervention itself. Secondly, you might want to see research respondents. For example, if you're assessing gender gap in financial literacy, for example, you cannot include studies that are only males, exclusively males, and you cannot include studies that are exclusively females. So every study that you do include have to be males and females, or males versus females. Secondly, you need to define the key variables, your outcome basically. For example, in this case, it would be types of financial behaviors. So you need to specify in the very beginning what financial behaviors am I going to include, for example, savings, financial planning behavior, and etc. Thirdly, you might want to also consider, fourthly, you might want to consider the research designs of the study you're including. So doing meta-analysis on correlational studies is actually quite difficult because it has a lot of assumptions relative to experimental-based studies, which are relatively easier to conduct a meta-analysis on. So you can either include both these designs or you can include one of these only. So I would recommend in the beginning you go for experimental studies only include experimental studies. It's much easier. Fourthly, you might want to consider cultural and linguistic range of the studies that you included. For example, you might not want to include studies from the Middle East if your research question is effect of juvenile delinquency on alcoholism, because you wouldn't get a lot of studies from the Middle East related to this topic, so you can exclude them. So this is you setting an eligibility criteria of studies that you want to include. You might want to consider the time frame as well. For example, financial education post-COVID-19 era. And publication types. You can include either published or unpublished research as well. Generally, to get published, for your meta-analysis to be published, it would be wiser to include both published and unpublished studies because published studies tend to be biased upwards. So the more The greater the effect that you find, the more significant your results. Obviously, your study is going to be more publishable in that case. And if you only include published studies in your meta-analysis, it can bias the results upwards. So that's why you have to include unpublished studies as well. Though if you do include published studies, you need to justify why are you including published studies only. So how do you identify and retrieve the studies that you're going to include in your meta-analysis? So I'm not going to go into details of this, but just to provide you an overview, firstly, you need a sample frame of potential studies that you do want to include. So you obtain the sample frame from relevant databases. For social sciences, Scopus or Web of Science, you can even consider Google Scholar. So on each of these databases, you then calibrate a search string of keywords that you write, and this keyword search has to be calibrated in such a way that maximizes the retrieval of your respective studies itself. And then once you have that sample frame of studies you have found from these databases, then you basically match it against your eligibility criteria. And then you start excluding studies against, once you match it against your eligibility criteria that we established before. So now that you have potential studies that you will include in your meta-analysis, what statistics do you require basically to conduct a meta-analysis? So this section deals with that. So in a meta-analysis, you basically need two things only. Everything else can be calculated from two things. First, you need an effect size. And second, you need the standard error of that effect size. Everything else can then be calculated. So the general rule is that you only extract one effect size from every study, not more than one, because there tends to be a dependency between effect sizes in one study, and that again biases your meta-analysis. So it's crucial that you only extract one effect size per study. So it's very seldom, actually only in 10% of the cases you will find that a study will report an effect size of, for example, of financial education on financial behavior. Most of the time, 90% of the time, it is you who will have to calculate the effect size. So the whole point of calculating an effect size is to convert the different studies into one common metric, which can then be aggregated and averaged out. And once you have the effect size and standard error calculated from each study, then you need to further calculate an inverse variance weight. So I'm going to go into details of each of these now. So how do you extract an effect size? So as I mentioned before, a critical step in a meta-analysis is basically to standardize every study into one common metric that you extract. So think of this as an example how physicists use the SI unit example. For example, 1 kilometer versus 1 mile. You cannot average out 1 kilometer and 1 mile. You cannot just add them and divide them by 2 because they're two different metrics. Similarly, when you download your studies, you will have beta values, you'll have t values. You cannot just add beta and t together and divide by 2. So you need to convert that into a common effect size. Now, there are different effect sizes to choose from, but in social sciences, most studies you will find two common effect sizes that you can choose from. The first effect size is known as a standardized mean difference, the most common example of which is called Cohen's d. So Cohen's d is the effect size you would choose to extract from your studies if your studies have a group design and they have a continuous outcome measure. So a group design is, for example, a between groups design or a within group design, in which you have a treatment group, you have a control group. In that case, you would use Cohen's d. So for example, the effect of financial education and intervention on financial behavior. So if you look at all these included studies on financial education intervention, all these studies have either a control group or an intervention group to compare the two results with. In this case, you would use Cohen's d, and financial behavior is measured on a Likert scale, more or less. So these are basically the standard units of interpreting Cohen's d. A small Cohen's d is known as a small effect when it's 0.2. It's known as a medium effect when 0.5, and 0.8 is known as a large effect then. So Cohen's d's values can be in the negative domain, and it can exceed 1. When the value exceeds 1, it just means greater than 1 standard deviation. So this is the formula for extracting and calculating Cohen's d. You take the mean of the control group, or the treatment group, and you subtract it with the mean of the treatment group itself. So control group minus treatment group divided by the pooled standard deviation. So this standardizes the difference between the two groups, and which is why it's known as standardized mean difference. So the formula is given over here. You just need to understand the formula. You don't need to basically memorize it, and I'll tell you later why. So you divide this difference by the pooled estimate of the standard deviation. The next effect size that is commonly used in social sciences is Pearson correlation coefficient R. Actually, there are different Pearson product moment correlation coefficients, such as bi-serial phi coefficient, but you can ignore this. Just concentrate on Pearson correlation coefficient. Now, this Pearson R value is used when you have correlational based studies that have an association between two continuous outcomes. For example, your IV, independent variable, is measured on a Likert scale, and your dependent variable is also measured in Likert scale. Now, when all your included studies are of this nature, then you should extract R effect size in this case. And the interpretation of which I have shown over here, small effect size 0.1, 0.3 is medium, 0.5 is large. Now, R values can also be in the negative domain. It just means that the correlation between two variables is negative in that case, inverse relationship. But R value cannot exceed, it doesn't exceed 1. So an example of this is that, let's say all the included studies assess the effect of financial education level on financial behavior. Now, financial education level is something that would be measured on a continuous scale. So in this case, you would use Pearson correlation coefficient. So this is the formula for Pearson correlation coefficient that you would use to calculate from each study. It's basically the sample covariance divided by standard deviation. So a lot of times a meta-analysis faces an issue where statistics are just not reported in studies. Actually, most of the time you will come across this issue that you need mean, standard deviation, t-values to calculate your effect size, but they're not reported. So in which case, what would you do in that case? So the thing is, with effect sizes, you can use a lot of different statistics to calculate your effect sizes, which is actually beyond the scope of this webinar, 1-hour webinar. But I tried to list the means for Cohen's d, which is the most critical metric itself. And for R, it's basically covariation, which you need. So you can calculate Cohen's d and R from a host of different statistics, even from t values, f values. So I have listed down a few references, which I'll get to later, and they have listed all the formulas which you can use. So a lot of times the statistics are not reported, in which case, what do you do then? So if the results are insignificant and results are not reported, then you quote the effect size as 0. You just write it as 0. Let's say study 1, when you're trying to extract the effect size, but you see that it is insignificant, the results relationship, and no statistics are reported then. So you just write effect size equals to 0. The second solution is that if results are significant and p-values are given, but the statistics are not given, let's say beta values are not given, then you quote the effect size associated with that p-value. I'll show you how to do this then. And thirdly, if the results are significant and p-values is not given, then you should use the minimum p-value of 0.05 to calculate your effect sizes. So how do you do this? So this is one example from Lipsey and Wilson's book. Why I'm actually recommending this book is because these distribution tables that they have given for imputing effect sizes is something that you cannot exactly find online. It's exclusively given in their book. So let's say that your included study used chi-square to assess their hypothesis, and you don't have p-values given and chi-square values are not given, then how do you extract the effect size? How do you extract Cohen's d in this case? Let's say they say that the results are significant and the p-value is given. Let's say the p-value is 0.05, in which case you will look at the table and see the associated chi-square value of 3.84. You would use this subsequent formula of Cohen's d to calculate your effect size then. And you can use R for this effect size then. But what if you note that the results are insignificant and no chi-square value is given? So then in which case you would use, let's say 0.8 if it's insignificant and they've given the p-value, and you would see the associated chi-square value. So this is just one way of calculating an effect size, or rather imputing an effect size. The next step after you have extracted the effect sizes, you need to then transform the effect sizes. For Cohen's d, it is often transformed into what is known as Hedges d. Hedges g. Cohen's d tends to overestimate the effect of the intervention for small samples less than 20. Hedges g then corrects for this upward bias. So you need to transform your Cohen's d then to Hedges g by using this formula over here. The important point to remember is that you need to transform your effect size. It's okay if you don't remember the formula itself. The next step is if you are extracting Pearson's R, you need to transform Pearson's R to Fisher's Z then, because Pearson R tends to be skewed. You cannot include these values in your meta-analysis. Your meta-analysis will be biased. So Pearson R is transformed into what is known as Fisher's Z. And this is the formula for Fisher's Z. It's basically the natural logarithm of this value over here then. So after you have extracted the effect size and you have transformed all your effect sizes, then you need to compute the standard error of your effect size itself. So standard error is a measure of precision around the mean. It's actually, you shouldn't confuse it with standard deviation, which is a measure of variability in itself. So a standard error tells you how accurate your estimate is relative to the mean itself. So for calculating the standard error of Hedges G, the formula is given here, and for Fisher's Z, the formula is given here. Again, you don't need to memorize the formula. You just need to know that you do need to calculate standard error for every effect size that you do extract then. And finally, you need the inverse variance weighting. I'll explain what this is. So the whole point of why you need this is because once you'll have studies that have different sample sizes. You'll have studies with very large sample sizes. You'll have studies with smaller sample sizes. So you cannot just average out all the effect sizes of all these studies together. Again, it will bias your results of your meta-analysis. Clearly, larger studies should carry more weight because they're more precise. Smaller studies should carry less weight then. So to go around this issue, Hedges 1983 proposed that the inverse of the variance should serve as the optimal weight of your effect size then. So what this basically means is that you take the inverse of your standard error, inverse of the variance that you just calculated, or 1 over standard error square. Since you calculated standard error, you take the square of that, that's your variance. So you just divide by the variance. And that is called inverse variance weighting, which then serves as a weight for each effect size. So you will notice that studies that have larger sample size have lower standard errors, and they then, if you carry the weight will be larger for these studies. So you just multiply this by the effect size, and that is you weighing against the inverse variance weighting. So just to summarize what we have done so far, or what you have calculated for your meta-analysis, first, you need to determine what effect size to extract, Cohen's d or Pearson's R. Second, once you calculate the effect size, one effect size per study, then you need to transform that effect size. Cohen's d is transformed into Hedges G, and Pearson R is then transformed into Fisher Z. And then you have to calculate the standard error of your respective effect size. And once you have the standard error, you can then calculate the optimal weight required. The fourth step is you need to develop a coding scheme. So the effect size is your dependent variable. Now that you have all the effect sizes from all the study, and your study characteristics are the independent variables. So study characteristics are basically the methods that every study has employed, the measures they've used, Likert scale, and so on, what treatment they've used, etc. So a meta-analysis should basically code all these study characteristics. It's important to do that. So you develop a coding scheme. How do you actually note down these characteristics of the studies, of your individual studies? So this is done in 2 stages. The first is called effect size level coding. The second is called study descriptor. So in the effect size level coding, you code everything related to a specific relationship that you're examining. For example, if you're examining the relationship between financial education and financial behavior, so in one Excel sheet, you will note down everything related to this effect size or this relationship. For example, the sample size associated with that particular relationship. In a second Excel sheet, you will note down everything that the study itself has noted down, let's say the overall sample size that the study used. Actually, more often than none, you will see that there are two different sample sizes in this case. So this is an example of what a coding manual would look like. You basically develop a coding manual, which is, think of it as your questionnaire if you're doing a survey research. This is sort of your questionnaire that you would follow. So it's important that when you code, you have numerical values. So if you look at ES type over here that I've written, so I've written this as effect size type. So what this means is what effect size I'm extracting from the study. So if I'm extracting Pearson R, I will code that as 1. If I'm extracting Cohen C, I will write that as 2. So you need to develop this sort of manual. Then you will see, let's say, for example, you're looking at the study characteristic, let's say race. You would code that. If your study includes greater than 60% white respondents, you would code that as 1. Greater than 60% are black respondents, you would code that as 2, and so forth. So this is just an example of what a coding manual should look like. You can make your own manual, basically. So you start with an effect size coding. So this is Excel sheet number 1, in which you note down everything that's related to the relationship you're examining. For example,
Hassam, sorry to interrupt you. The previous slide, it was too small.
Really?
Mm.
Zoom in.
Sure. Yeah. Yeah, it's good to zoom.
Right. So,
Later, can we have your slides?
Yes, I can send all of this.
Thank
you. Is it visible now? Is it more clear?
Yes, I can. I can see now. Yeah. And if
Right.
you send me, you email me your slides, I will send it to all participants.
Right, I will do that. So just to recap, this is what a coding manual looks like. So you have, let's say you're trying to extract education level of respondents. I'm just going through it once again so that you guys can see it properly. So let's say the education level of your study, most of the respondents are primary school educated, the highest education level, let's say more than 60%. So you would code that as 1. So your manual informs you what you should do and how you should code. It's good to have this sort of manual. Right, so I'm just going to move on to the next slide. So yes, you have 2 coding sheets now, two Excel sheets. So one is effect size level coding, in which you code everything related to a specific relationship that you're trying to examine, which would be the sample size used to examine a specific relationship, the variables used, financial behavior, for example, financial education. So you would note down what is the independent variable, what is the dependent variable, and it's very important that you note down the page number that you extract all this information for. Your Excel sheet number 2 is the study descriptor. So everything that's included in the study would be noted down in your second Excel sheet. Now the second Excel sheet, study descriptor level 2, is very similar to what you would do in a systematic review. So you would note down everything, the type of publication, the mean age, the predominant race, the sample size of the entire study. So it's important that you have 2 separate sheets, Excel sheets. And once you're coding, you can also establish what's known as a coder reliability. Most of meta-analysis actually have this section in which they try to establish reliability of your coding protocol in itself. So if you have only one person who's extracting information, you can still establish a coded reliability by drawing a subsample of the studies that you coded and coding it all over again to check how accurate you were. So if there were 2 coders, then 2 coders would independently extract information and compare the results. It doesn't have to be all of the studies. It has to be it can be a small subset of 20 studies, or let's say 50 studies would be more than enough. You can even quantify this coded reliability, which is known as kappa. I'm not going to go in details into that because most studies actually don't include this sort of quantification. But if you do want to include it, the terminology is called kappa. And finally, moving on to the analysis section. So analysis consists of 4 parts. You need to determine the type of model. You need to then report your summary results. You need to do what's known as a publication bias assessment, and finally a moderator analysis. Now, unfortunately, everything that we have done up until now can be done manually or on an Excel file, even for that matter. But the analysis part, you really do need a specialized software to do it. There is no way of going around it. So this is what your final data set should look like. If it's not clearly visible, please let me know, yeah? So I can zoom in then. So after all your extraction of all your information, your Excel sheet should look like this.
Yeah,
so
please zoom in, Hassam.
yeah. Right. So let's say you have steady ID number 8, whatever that steady is. You would write down the effect size number you have extracted. And in this case, I extracted hedges G. I write down the value of hedges G. Next is the standard error, then the variance. If you know the standard error, you just take the square of that and that's your variance. And then the inverse variance weight, which is denoted by W over here, which is simply 1 divided by the variance itself. Now, this is the effect size related information that you have extracted. On the right columns over here, PUB, TF, you don't really need to know what that means, but these are your categorical variables. These will be used for a moderator analysis that you have already coded in your Excel sheet. For example, publication type, I will code that as 2 if it's a published paper, and I'll code that as 1 if it's an unpublished paper. Next, let's say, for example, G and gender. I will code that as 1 if it's male and code that as 2 if it's female. And OUC is outcome category. Let's say outcome category 5 represents savings, number 3 represents financial planning behavior, and so forth. So this is what your Excel sheet should finally look like. So after that, you have to determine, in the analysis, you have to first determine the type of model. You can either use a fixed effect model or a random effect model. So most of the meta-analysis papers don't use a fixed effect model. The assumption of a fixed effect model is that the true effect size is basically the same for every study, and any observed difference in the effect size is purely attributed to the sampling error itself. So this is a very wild assumption to make, which doesn't hold in the real world, which is why most meta-analysis move on to a random effect model. So in a random effect model, it is assumed that the true effect might differ from one study to another study, and the true effect differs because of study characteristics. And this is exactly what you want to examine then, that why do the effect sizes for every study vary? Why do they differ? That is done in a moderator analysis. It accounts for that variation in effect sizes, conditions under which the effect size differs. So if you're unsure which model to proceed with, it's always safer to do a random effect model. You can never be wrong with a random effect model. Next, you need to report your summary results. What that basically means is that you need to report your aggregated effect size, the combined effect size. So this is something that's done in a specialized software. For example, you would use a package known as Metaphor in R. I'll explain that later. So what you need to report is the mean effect size, the average effect size that you accrue from all your studies. That will just be one effect size. The associated standard error of that effect size, you will write the p-value, whether the effect size that you have found of aggregating all these results, if that's significant or not. The confidence interval, associated heterogeneity. So you can actually quantify the heterogeneity. I'll show you how. And then cases analyzed in forest plot. So if you look at table 5 over here, this is an example of a random effects model that the results of which you can get from so using our software Metaphor package. So the important points over here is the estimate. This is your one estimate of effect size, the aggregated effect size that you have computed. Next, you need to report the standard error, which is written in SE over here. And CI, and the both CIs over here is the upper confidence interval and lower confidence interval. You need to report this. You need to also report heterogeneity, the I square value over here and Q value over here. These two basically you need to report. So heterogeneity basically tells you how heterogeneous the effect sizes are in your studies. So basically in this study, 97% heterogeneity, your effect sizes are basically heterogeneous by 97%, which is quite large. So Q is also a way of quantifying heterogeneity over here. So a significant Q value basically tells you that your effect sizes are very heterogeneous and you may now proceed with a moderator analysis. So to explain what accounts for this heterogeneity, you would then do a moderator analysis. So you also need to make a table and note down summary results. Let me zoom in so you guys can better see it. This is the second thing that you would write down in your results. So let's say there's study 1. Actually, let's look at study 7 by Yang 2018. You would make a table and you would write the effect size that you extracted, the upper and lower confidence interval. You don't need to write the weight, you can ignore that. But you need to write this down in your results section for every study, the effect size that you have extracted. Oops. And then you need to also show a forest plot. This is what's known as a forest plot. Is basically a graphic representation of the results of your meta-analysis. So how a forest plot works is that if you can see this vertical line over here, this is known as a line of null. Anything that's on the left side, these points that are on the left side favor the control group. Anything that's on the right side favors the treatment group. So this is you establishing whether an intervention was effective or not. So if you can see how wide these individual points are, this is your confidence interval, basically the upper and lower confidence interval, 95%. The more wide the confidence interval, it shows that the higher your standard error value was large, which means that the steady sample size was small. So the more spread out this points over here, that means the less precise that study was. And if you can see the center dot, the larger this dot, these black dots, it means that the study carries more weight and it's more precise. And number 41, if you can see over here, this is your final effect size of accruing all these studies together. This is your mean effect size that you report. This is why you conducted a meta-analysis, basically. So the second analysis you need to do is known as publication bias assessment. So publication bias is the greatest threat to your meta-analysis results. So publication bias means that you have only included certain class of studies. You have not included every study. So you can quantify and visualize whether your meta-analysis has publication bias or not. So it's important to do this step. For example, if you only include published studies, your publication bias assessment will show that there's something wrong with your meta-analysis. So this is how you visualize a publication bias. This is known as a funnel plot. So a funnel plot is basically on the x-axis, you have your effect size. On the y-axis, you have the standard error. So up until now, everything that we have done until now, you always needed two statistics. You needed this effect size and you needed the standard error. Basically with that, you can do everything then. So a funnel plot is basically a scatter of the intervention effect estimate on the individual studies. So it tells you how precise every study was. So the more precise your study, the higher it will lie on these points over here, basically. The higher the estimate, standard error estimate is, the lower these points over here. So the idea is if you have publication bias, it will lie outside these points over here. And you can visually see that. Again, this is done by a software. This is not something that you can obviously manually do. So this is one way of visualizing a publication bias. In this case, there is no evidence, visual evidence of a publication bias because these points seem to, most of them seem to fall within this funnel plot over here. You can also quantify a publication bias by doing two different tests. I'm not going to go into details, but just so that you guys know what it is. The first type of test is known as Baggin-Bozumber's RAG correlation test. It's basically you correlate the intervention effect with the standard error. If this p-value is significant, it basically means that you have only included one type of study with the same sample size. So you need to have, it's good to have a mix of studies that have small sample size and large sample size. And this p-value will tell you whether you included studies that only have large effect sizes or small. The next is Eagers regression test. This is a way of quantifying publication bias as well, which is pretty much you regress the intervention effect against the standard error over here, the weighted standard error in this case. Again, if your p-values are non-significant, it shows there's no publication bias. So if I move back over here, you see this vertical line. This is what Eagers regression test shows you. It shows you how much does this vertical line deviate from zero. The more it deviates, the more the evidence is that there is publication bias. If this is zero, it shows that you have absolutely no publication bias. Finally, you move on to the moderator analysis. So the whole point of doing moderator analysis is to account for the heterogeneous effect sizes. Why are there heterogeneous effect sizes? Or you can also say conditions under which there are heterogeneous effect sizes. So this is the whole point of doing a moderator analysis. And this is done in a random effects model. You don't do this in a fixed effects model. So there are two ways of doing a moderator analysis. First is meta-regression. Second is known as analog to the one-way ANOVA. So meta-analysis, meta-regression is more advanced, so I won't go on that. So I'll just talk about analog ANOVA method for performing moderator analysis. So this is very similar to doing a one-way analysis of variance. I'm sure everyone has pretty much done that. But in a meta-analysis, what you do what is called as an analog to ANOVA, in which you have exclusive, mutually exclusive categories of, let's say you have gender. One is male, you code female as 2. So this is you creating your independent variables in this case over here. So once you have these categories, you can proceed with an analog to ANOVA. This is how you would report your results. And this is something that can be done on SPSS, but you will need a macro for that, which is known as Wilson's SPSS macro. This is something that can only be done on syntax, SPSS syntax, but this is how your output would look like. Over here, this is actually, if you look, it's very similar to a one-way ANOVA, but the important thing over here is you need to look at this between over here. If this is significant, this tells you that, yes, the categories significantly explain heterogeneity in your effect sizes over here. And the category over here, 1 was male, 2 was female. So you just need to look at this p-value over here, and it tells you whether there's a moderating effect or not, whether these categories, male, female, explain any very heterogeneity in your found effect sizes. And this is how you would write it. Gender, for example, significantly moderated the persuasiveness of gain and loss rate messages. So you don't need to go into that. You just need to report the Q value over here. The Q value is given over here between Q. This is the heterogeneity value. And the P value was significant, it was less than 1. So yes, so what softwares do you need to actually do all these analyses? I have listed the softwares here. Maybe you can take a picture or screenshot this, or I think Dr. Said will share these slides with you. Just go ahead. So you can see these are the packages that you can use for doing your meta-analysis. So there are some online calculators. There are 2 famous online calculators that you can use. But the problem with these online calculators is that you can calculate the effect size, but you cannot calculate the standard errors with them. I would recommend using R package in this case. Actually, it's not that difficult using R. You just need to know a very basic programming, which you can then do a meta-analysis. So a lot of social science meta-analysis use this package called Metaphor. Actually, 90% of them use this. This is the recommended package for conducting a meta-analysis. But if you don't use R, you can't use R, you can use SPSS. You can download what's called Wilson's macro. I've listed it over here. But you will need to know how to use SPSS syntax. Without that, you cannot do it. And actually, even when you download these macros, it comes with instructions. There's actually YouTube videos also on how do you conduct the meta-analysis, then the analysis part. But for all this, you will need the effect size, and you will need standard error for each effect size. And then rest, you can compute everything basically. So for further readings, I would highly recommend, if you are actually interested in doing a meta-analysis, to buy this book by Wilson and Lipsey. This is basically, think of this as the Bible of meta-analysis. Everyone uses this in social sciences. So I would highly recommend this book. And you can screenshot this, or the slides will be shared to you. Yes. Yep, that's about it. Thank you. And I think we should move to the questions, I guess.